Good evening. We're going to do something a little bit different to start out because I just got a new molecular model set. So I was thinking that we could go through this together and simultaneously we'll be talking about VSEPR. Valence shell electron pair repulsion theory. So this particular kit, this one is advanced chemistry. And so what that means, I'll open this up, we can see. Is that it has, let's see, it includes pieces like this. Here, let me move this so you can see it better. And notice how this is for an octahedral structure, like a metal center. So this would be considered advanced just because it's a little bit more complex than when you're doing organic chemistry. And a lot of your carbons are sp3 hybridized, giving you the tetrahedral structure like this one. This particular kit also, I noticed, let's take a look. It includes, look at this one out, this trigonal bipyramid. So this is when you have 5 ligands or 5 elements, which gives rise to the axial positions and then the 3 equatorial positions. Trigonal bipyramid is also included, as well as square planar. So notice how for tetrahedral, this is when there's the central atom and 4 other atoms are around the central atom. But it's 109.5 degrees. But with square planar, we have 90 degrees, even though there are 4 other atoms around the central atom. Due to there being lone pairs here and here on either side, that gives rise to square planar. For something like if we have a central atom that's iodine, there's different possibilities there, some of those larger atoms. And we also get square planar structures for metal centers, such as platinum +2. And the reason for that is a little bit different. It's not necessarily that there's lone pairs above and below, but it has to do with the stability that results from there being 4 ligands around a metal that has 8 d electrons. So it's something you learn about if you take an inorganic chemistry course or coordination chemistry or something like that where you're focusing on the transition metals, you can learn about those more. I also notice, I'm digging in here more. Let's look a little bit more. This is kind of fun. Not a lot of model kits have these different kinds of structures. So this one here, what is this? Okay, this is a tetrahedral, but notice they made it gray colored like a metal because some metal centers do have tetrahedral structures. So while you could just use the center that's black, the convention is that black is used for carbon and silver is used for metals. So this is fun because it actually has the silver colored. Oh, these are getting difficult to get out. I have to dig them out. They're kind of slippery. Okay. This is an unusual shape for a metal. This is trigonal planar, which you do see for something like boron trifluoride, but not quite as often do you see it for metals. So, but they did include it, as well as linear. So this would be an example of a metal that has this linear shape. It's a very deadly metal complex. Mercury that has two methyl groups, dimethylmercury, that can cross the blood-brain barrier. So if you get it on, even you're just, you don't need very much at all, picomolar, nanomolar, makes it through your skin and gets into your blood, and it can make its way to your brain. And anyway, I'm not going to get too negative here, but it is interesting to know some of the biochemistry as well as the chemistry of many of these compounds. And especially the metal centers, they're just not as common as our organic compounds. So this kit has these different shapes. It's pretty cool. And we can build some things with these and just get an idea about this. This kit is different than other ones that I've seen. So we can see how it is different and see if we like it. So I'm going to put the metals down for now. You can put them over here. Okay. So let's take a look. Here's our carbons that are tetrahedral. I can put these here. And what else do we have? So notice here we've got some atoms that might be like the peripheral atoms on the outside, because they just have one place to attach. So I assume that this orange is meant to be sulfur. That's common, doesn't have to be, but it's commonly used for that. You could also use it for bromine. And sometimes the main thing is to just have a different color so that you can distinguish it from other ones. So our purple here, you could use that for iodine, if we want to distinguish the halides from each other. In fact, let's do that, because we also have this yellow one and this green one. So we could show this yellow one being fluoride, green being chloride, orange being bromine, and purple being iodide. And we could make a stereocenter. So looks like these are how you connect these connectors to make the bonds. Are these gray tubes? I'll move the metals over. So these gray tubes you can put the atoms in, and looks like they have some black. These are a little bit more rigid, so these black ones, you can see these are not moving. Whereas this short gray one, it's a little bit more squishy and I can bend it. Okay. Let's see what else there is. This is a longer gray one, so maybe this is for creating a pi bond. So you can see this one's pretty bendy and bendable. And here's some other one more. I think it's the same length as this one, but it's bendable. Okay. So let's see. Let's create a chiral center out of one of these carbons. It's a tetrahedral carbon. So how about if we put one of these bonds and attach it to each one. And then, what we could do is we could make both stereoisomers. Make them mirror images of each other. Okay, so here's our carbon atom with the 4 bonds, and then we should put something at the end of each bond, right? Oh, look, I was trying. One of my colleagues had some nail polish that he was using to paint some 3D printed proteins, and I was like, hey, I had my nail polish chip off, can I put the purple on there? So I have purple, red, silver, and gold. Anyway, okay, let's build our molecule. Okay, so we'll put fluorine here. And I'll put a chlorine on here. And then we'll put a bromine. And in the last position, iodine. Okay, so here's our little molecule. So this is an analog of methane, but instead of hydrogens, we've got bromo, chloro, fluoro, iodo in each one of those positions, methane. Okay, now what we can do, I'll get 4 more bonds. So put these bonds on. And now we will make the mirror image. So if I face these towards each other, that tells me that I need to have the chloro there and the iodo over here, right? And then I'll put the fluoro up there. And bromo atom back there. Okay. So notice how these are chiral, 2 chiral centers, and they're stereoisomers because they are non-superimposable. So just like our hands are mirror images of each other, these mirror images. And if we tried to superimpose one on the other and say, oh look, these are identical, if we tried to say that, look, we just stack them next to each other and we see, nope, they're not. Because while in this case we have the iodine, or say, I should say iodo atoms over here, and our fluoro here, these are not the same for these 2 atoms that are bonded. They're reversed. Okay. So these are different. They are chiral isomers, stereoisomers of each other. So these will be optically active. So what would be an example of something that was not optically active? So let's look at if we were to remove these bromine atoms. And instead of there being bromine atoms, let's put fluorine. We designated fluorine as yellow, so put yellow there and there. Okay. So now let's see. Are these now still chiral centers or not? So we take a look and we go, okay, let's see. 2 of those are the same. These 2 are different. Is there some way that we can orient these where they are the same? Or can we not? So we try to move them around. This is if we're reasoning through this problem. We try it this way and we go, no, because these are opposite positions, but these are the same, these are the same. And you can try turning it out this way. Aha! Look at this. We turned them around in such a way that now we see these are superimposable. See? We've got yellow, 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 green, green, blue, purple, purple. So these are identical molecules. They're not isomers. They are two of the same thing. Okay? So once you have removed these bromines and you made two of those attached atoms the same, you have increased symmetry and it's no longer chiral. So that's definitely one thing to remember with our tetrahedral centers, that when all four are different, right there is your clue that it will be a chiral. But even just making two the same, nope, no longer. So I started doing that kind of on a whim. I think it was good to go over. So we were doing two things. One, we're going over chirality, and the other one was we were just checking out this model kit. So I'm really curious about, because some of these model kits, they kind of bug me, honestly. When you're doing things like making carbon dioxide, and I just feel like the double bonds aren't truly representative of what the bond should look like. But there are some things that do work. So let's check that out. Let's make carbon dioxide with this kit and see how well it works and see if it makes sense for us. Okay, so carbon dioxide. The convention, once again, carbon black, and oxygen convention is blue. Now this is the thing, if you run out of blue and you need to use another color, that's totally fine as long as there's the right connectors to them. So, oh, and I'm sorry, I totally misspoke. Let me get this just a second. Blue is used for nitrogen. Those of you who are watching and going, what are you talking about? Blue is usually used for nitrogen. You're right. I'm so glad I caught that, because that would just really bug me if I made this whole video saying that blue is oxygen. Again, this is just convention, and this is actually a really good example of how you can swap out different pieces and they're still going to work, just as long as you're clear in your mind which atom it is that you mean it to be. Okay. So let's put these little nitrogens over here, because we'll make something with nitrogen soon. But we'll just leave it there. Okay. Okay, but for now, let's make carbon dioxide. Alright. So we've got our carbon, and we've got our two oxygens, and once you've drawn the Lewis dot structure, you then identify that there are two double bonds. And so the way this model kit works, which is similar to many others, is that to make double or triple bonds, you use the bendy ones, the long bendy ones, to show that it has double bonds. So what we can do is put it onto a carbon and then attach it to one of the oxygens. I'll get another one here. And this is when we bend it. So we now plug it in, and here's when we bend it. Let's see. And we have now created a double bond. So what this is showing really is just the pi bond. It's not showing the sigma bond that's between the two atoms, but you still get to see the double bond at least. So just don't forget there's also a sigma there. Okay, now we can do the same with the other oxygen, and you'll see here that in the other plane are these other locations to put in the bonds, which is good because those pi bonds are in another plane that's orthogonal to this one. So it works out. Okay, we're not quite there yet, so it looks a little funny right now. But once we add in our oxygen, and then again we bend it, and then we put it in. I'll get in there. Insert it. Okay. And there we are. Here is our carbon dioxide, showing the pi bonds that are perpendicular to each other. And these little nibs that are sticking out, these you could think of as, these are showing the lone pairs. Here and here. Okay, so there's another molecule that we got. Okay, how about our trusty nitrogen? So why don't we build a little ammonia molecule. So we'll just have NH3. So we've got 3 of these locations have bonds, and then put on our hydrogens. So hydrogens convention is that they are white. So I got 3 of these. Okay, and why just 3? Why not? I guess I should ask, why did I take a central atom that's tetrahedral and not one that is trigonal planar? Like here's an example of a trigonal planar where the molecule would be flat. Well, for nitrogen, if you add up all of the electrons that exist for ammonia, nitrogen, in fact I could look at our periodic table, and we see nitrogen's in group 5, so it's got 5 valence electrons. Hydrogen, each of them has 1. So if you add those all up, it's got 8 electrons, valence electrons total. And so we have a pair here, so there's 2, 2, 2. And that means there needs to be another pair of electrons right here. So, according to VSEPR theory, this pair of electrons is going to repel the other pairs in those bonds. It will create this trigonal pyramid shape. It will not create this flat trigonal planar because there's a lone pair up there. So there's our little ammonia. Okay. So this is kind of a cool kit. I think I'm liking it. I'll show you a little bit right here. So as I said, it looks like these here are for if you're putting a halide at the end, like what I call peripheral atoms. Then you also have a bunch of these carbons. So if you have organic compounds or something, you have these tetrahedral carbons. You've got some of my favorite things. These look like jacks, don't they? But we have octahedral, we have a linear, square planar, all those that we looked at earlier. And we've got a bunch of these short bonds. And then, what are these? It's like we have these colors again. We've got to be able to put a bunch of oxygens in our molecule. That's handy. And our blue for nitrogen. But we do have these fluorines that are usually yellow, and chlorines that are usually green, but you could really use these as anything. Alright, well, thank you so much for joining me. This has been so much fun, and I will see you again very, very soon.